Okay, in the world of metal fabrication, structures repair, engine repair, exhaust repair, you may come across a attachment procedure called welding. Welding is used across the world for any number of fabrication or fabrications, I should say. And the aircraft are no different. There's plenty of welds on aircraft that happen in the components, on the structure, and on the power plants. Now, if I'm being honest, there's not a whole lot of welding that you will do as an aircraft mechanic. Most of the time, if you come across a need for some welding to be done, you're going to send it out to another shop and to a welder who welds things all day long, not just aircraft, but just whatever. In certain airports and certain operations, they might employ a welder who's not an A&P or anything else like that, and they just come out and they weld whatever needs to be welded if they see enough volume for it being needed. Now, it's a good skill to have for fabricating things around the shop. Like I say, if you needed to build a specialty stand for an aircraft that y'all are working on, welding is a good way to go about doing it, and having that skill set in your back pocket makes you a value add to any team that you're coming on. But the possibilities of you actually welding on an airplane is pretty slim. It can still happen, but I'll tell you, I've been an aircraft mechanic. I've been in the world of aircraft maintenance since I was 16. I'm 37, and I've never once welded on an aircraft. I've taken exhaust off to go get repaired by a welder. I have installed long-range fuel tanks that were built by a welder, but I have not, nor have ever seen anybody actually weld directly on an airplane, and that tends to be the actual case with most aircraft mechanics. That being said, it's a good skill to have, and it could absolutely be employed on an airplane in certain circumstances. But more often than not, if you're at the point that you need to weld something, outside of the world of maybe piston engine exhaust or big heavy commercial engines have a lot of aluminum welding that ends up having to have happen. Out of those kind of scenarios, most of the time it's just a component replacement, or you send it out to the shop. So don't think that you're going to be welding on a regular basis as an aircraft mechanic, unless you decide you want to be an aircraft welder and you can build a business that way. But that being said, we're still going to cover all of the kind of the world of welding, and we're going to talk through it. And it very well may show up on any one of your exams, and it may show up in your later career where knowing something about welding is very useful to you. So buckle up.
Okay, so to get us started, let's just talk about some of the gases that you could potentially encounter in the wide world of welding. First off are what's known as shielding gases. Now, these are gases that protect the weld from any kind of damage or interference as a result of contact with the atmosphere and all the gases that are in it. So you can think about it like this: whenever whenever you want to create a weld, that weld is still in its liquid form. It still can be influenced by things it comes into contact with. You want to make sure that it's all filled up, so that way, or that the area that it's around is completely inundated with a gas that's not going to interfere with it. Kind of like if you have a kid, you want to make sure that he's running around with the right crowd. You don't want to have any bad influences that cause him to go astray. You want him to hang out with good kids that do good things. That's kind of the idea with shielding gases. So the first one that we're going to talk about is argon. Now, argon is a colorless, odorless, tasteless, and non-toxic inert gas. Inert gas cannot combine with any other element, and it has a very low chemical reactivity and low thermal conductivity. It's used as a gas shield in the electrode in MIG, TIG, and plasma welding equipment. So essentially, you're going to use argon to push away any atmospheric interference into that weld while the weld sets up. So the first shielding gas that we need to know is argon. All right, for those of you that aren't familiar with argon, you should absolutely be familiar with helium. Now, helium is another inert gas that's colorless, odorless, tasteless, and non-toxic. Its boiling and melting points are the lowest of all the elements, and this normally exists only in gas form. It's used as a protective gas shield for many industries, to include electric arc welding. This is the same gas that comes in balloons that you can inhale whenever you're like a little kid and talk like a chipmunk. But it also gets used as an inert gas for welding. Okay, another one that's really commonly used is carbon dioxide. Now, carbon dioxide is typically mixed in with one of the other gases, so you'll get a mixture of it. It helps improve the weld speed, the penetration, and the mechanical properties of the weld. So you typically won't see all carbon dioxide, but it could be included in the gas mixture that's being used.
Okay, so that's all there really is to shielding gases. Essentially, you're going to have your wire stuck out, and the gas is going to come out and form a little shield, an atmospheric shield around that wire as it contacts the metal and melts and creates the puddle that becomes the weld. It's really not that difficult to figure out. So now let's transition. Let's talk to flame welding gases and what they look like.
Okay, so there's two primary gases when it comes to gas welding. First is acetylene. Now, this is the primary fuel for an oxy-fuel welding and cutting. It's chemically very unstable, which means it lights off really easily, and then it's stored in special cylinders designed to keep the gas dissolved. The cylinders are packed with a porous material and saturated with acetone. When the acetylene is added to the cylinder, it dissolves, and in this solution it becomes stable. Pure acetylene stored in free state explodes from a slight shock at 29.4 pounds per square inch. And the acetylene pressure gauge should never be set higher than 15 psi for welding or cutting because it is really unstable. Now, the other primary gas is oxygen. Now, oxygen gets used in the welding process to increase the combustion rate, which increases the flame temperature of flammable gas. A lot of times, you'll see these acetylene torches that are paired up with oxygen bottles right next to them, on a little cart, just like you're seeing now. This one looks like it came out of the 1800s. Most of them don't look that old, but that's essentially the two main gases that you'll get. There's also the potential that you could use hydrogen. It's a colorless, odorless, tasteless, and highly flammable gas that can be used at higher pressure than acetylene, and is used for underwater welding and cutting. It's also used for aluminum welding using the oxygen hydrogen process. Now, if you're welding on an airplane underwater, I want you to email me because that's a really interesting story. I've not seen hydrogen used on aircraft. I mean, frankly, I've not seen a whole lot of welding done directly on aircraft. Most of the time, it's on stuff that's off the airplane in a shop somewhere else.
Okay, so when it comes time to actually move one of these cylinders, we want to keep a couple of things in mind. Number one, they should always be upright. This is especially true with acetylene because inside of the acetylene, there's an absorbent material that helps grab the acetylene and keep it inside of the container. If you turn it on its side, it'll leak back out into all your hoses and all the good stuff, and it can cause a flashback. If one ends up on its side, it needs to stand upright twice as long as it laid down. So if it laid down this way for a day, it needs to stay upright for 2 days before anybody touches it to make sure that it is safe to use. Now, once we have it in the shop, there's only two real ways to store it. One is upright next to a wall with a chain, making sure that it can't fall over. Or number two, it needs to go on a mobile cart, also chained off. That's why most of the time you see flame welders on little carts that can be moved around.
Okay, so now that we understand the different gases and how they work, let's talk about inert gas welding and the procedures that go with it. Now, a lot of times you'll hear this referred to as arc welding. Arc welding is effectively the family in which inert gas welding happens, but whenever you introduce a gas into it to help shield the weld, it technically becomes gas metal arc welding, or GMAW. Now, that's the new term. It used to be called MIG welding, metal inert gas welding, MIG. You'll hear a lot of people refer to MIG and TIG, but that's all the same thing. All right, so what is MIG welding or GMAW welding? Well, effectively, it's simply what you see on the screen right here. You have two pieces of metal that you're trying to weld together. You're going to take a nozzle that's going to distribute a shielding gas that comes out, and then the center of that nozzle is going to be a little wire that sticks out called a consumable electrode or welding wire. That's going to come out. It's then going to superheat to the metal, melt, and then join those two pieces together. And I'll do it all via electricity. Now, this type of welding is really effective at in manufacturing environments. You can do a lot of welding pretty quickly with it, but it's not really super effective when it comes to repair work. Reason being is that the only way to test and make sure that you have a quality weld is through destructive testing. So it doesn't do you a whole lot of good to spend all this time welding on it if you have to turn around and destroy it just to be able to determine that you did a good. Okay, the type of welding that is actually is done on aircraft, both for repair and manufacturing, is TIG welding. Now, TIG welding stands for tungsten inert gas, but nowadays it's supposed to be referred to as a gas tungsten arc welding. Though you'll always hear people say TIG. Older folks might refer to it by the brand name that came out with it, called Heliarc or HeliWeld. It's all the same thing. So if you hear any of those terms thrown around, they're all talking about just TIG welding. Now, in TIG welding, the electrode is a tungsten rod that forms the path for a high amperage arc between it and the work to melt the metal at over 5,400 degrees Fahrenheit. It's pretty hot. The electrode is not consumed and is used as a filler, so the filler rod is manually fed into a molten puddle in almost the same manner as with a oxyacetylene torch. A stream of inert gas, such as argon or helium, flows out around the electrode and envelops the arc, thereby preventing the formation of oxides into the molten puddle. So essentially, what you're doing is you're causing an electrical short that's heating up the that electrode there, and then you're going to take the filler metal and then just stick it in there, and that's going to help melt it onto the work, and then thus melt it as it cools and melts it into those two pieces of metal. That's where you get your actual weld from. The gun that you're going to be holding doesn't necessarily feed the rod like it does on the arc welders. It just allows the electrode to get hot and the gas to flow over it, so that way you have a shielded gas going into it. It's pretty simple, pretty standard way of welding. So modern TIG welding machines are offered in AC, DC, or with an AC DC configuration, and either use transformers or inverter-based technologies. So typically, these machines are capable of AC output that's required for aluminum, but the TIG torch itself has changed very, very little over the years. They've simply just added more robust capabilities to it to be able to weld more and more metals. Now, the shape of the electrode in TIG welding is very important if you want to maintain quality and have the right penetration of the weld, which is effectively the quality of the weld. The tip of the electrode should be shaped on a dedicated grinding stone or on a special purpose tungsten grinder to avoid contaminating the electrode. Remember, this is a game of making sure that the weld doesn't get contaminated with anything outside of what you want to be on there. That's the whole purpose of the shielding gases and everything else. The grinding should be done longitudinally, not radially, and with the direction of the stone travel away from the tip. Now, this table will show the effect of a sharp versus blunt electrode with transformer-based machines. So, effectively, like you can have a sharper electrode is easier to arc, doesn't require as much amperage, is wider, has good arc stability, but it does have less weld penetration, and it does have a shorter life. A blunter electrode, on the other hand, is going to be a little bit harder to start and get going, but it does handle more amperage. It's a little bit narrower, but it has the potential to wander. So it's going to require a more skillful welder, a more attentive welder, but it does last longer and have better penetration. So you can kind of make those make adjustments to the electrodes as needed as you progress on in the job. Now, TIG welding is really versatile. You can use it for aluminum, you can use it for stainless steel, steel tubing, titanium, magnesium, all sorts of things. But probably the coolest part about it is its history. Now, TIG is really an American story. It was first developed in the 1920s by General Electric, but then perfected on the XP-56 program by Northrop, specifically the helium shielding gas and the tungsten electrode. They needed a process that was developed for really welding magnesium to the flying wing on the XP-56 that would also help eliminate the corrosion and the porosity issues with the atomic hydrogen process they've been using with boron flux. Now, it wasn't really used on the other materials until the 1950s, whenever it found some merit in welding space-age superalloys, and then later on to other metals such as aluminum and steel to a much greater degree. So, really, the innovation of the XP-56 program gave us TIG welding, and even after the XP-56 turned out to be kind of a dud and never really see the light of day, the space race picked up the TIG welding and then really ran with it. When you think about having to weld titanium, there's just not a whole lot of things out there that can do that. So it's pretty awesome that that they figured that out.
Okay, here's a couple of things to think about whenever you're about to engage in some sort of stick welding. The questions that you need to ask yourself. First off, do you have the right PPE? Think about this, like there's high levels of electricity, heat, molten metal and stuff. You want to make sure that you're properly covered, both with your eyes, your shield, your gloves, and make sure that you're not grounded to anything that's going to cause you to get shocked. Second, is the ground connection been properly made to the workpiece, and is it a good connection? You want to make sure that the machine is grounded itself. If not, that could be a hazard to yourself, and also you're not going to make a very good weld that way if you don't have it grounded. Has the proper type and size of the electrode been selected for the job? I remember we went over the different types of electrodes, the blunt, sharp, and different. And there's a variety that you can choose from. Is the type of electrode you're about to use applicable to that job? All right, is the electrode properly secured in the holder? That could also cause you some problems. Make sure that your equipment's secured, vital to any job, but especially with welding. Does the polarity of the machine coincide with that of the electrode? It's another good thing to check on. Is the machine in good working order, and is it adjusted to provide the necessary current for the job? And remember that your machine is really kind of it's key to all of this. If your welding machine is not working properly, or it doesn't have or it's not set on the right setting, or it's not capable of delivering at the right setting, you're not going to make good quality welds. And best case scenario, you just got to waste your time and get frustrated. Worst case scenario is that you do what you think is a good job, but it actually fails later on, and you've wasted a lot of time and potentially endangered somebody.
Now, correctly striking an arc is going to take a lot of practice. The main difficulty whenever you first get going is the arc sticking the electrode to the piece that you're working on. Now, if the electrode is not withdrawn promptly and upon contact with the metal, the high amperage flows through the electrode, causing it to stick or to freeze to the plate, and it practically short circuits the welding machine. So a quick roll of the wrist, either left or right, usually breaks the electrode loose from the workpiece, and if that does not work, unclamping it from the holder, from the electrode, and turning off the machine gives you the ability to work on it a little bit further, using a small chisel or a hammer to knock it loose from the metal. Now, then after that, you can turn the welding machine and go back on. Now, there's basically two ways to strike an arc. This is the first one that you're looking at now. It's called the tapping method or the touch method. So when you're using this method, the electrode is held in a vertical position, so it's straight up and down, and lowered until it's about an inch or so above the point where the arc is going to be struck. Then the electrode is lightly tapped to the workpiece and immediately lifted to form an arc approximately about a quarter inch in length. Okay, the other technique that you can use, which is usually a little bit easier, is the scratch or sweeping method. To strike the arc by the scratch method, the electrode is held just above the plate at a 20 to 25 degree angle, and the arc should be struck by sweeping the electrode with a wrist motion and lightly scratching the plate. The electrode is then lifted immediately to form an arc. Either method takes a little bit of work, but with time and experience, it becomes easy. The key is to raise the electrode quickly, but only about a quarter inch from the base, or the arc is lost. If it's raised too slowly, the arc sticks to the plate. So that's always, you're either going to lose the arc or you're going to stick the rod to the plate. Neither one of them is what you want. You want it to just be able to go over it over and over again, so that way it can continue to weld. Now, to form a uniform bead, the electrode must be moved along the plate at a constant speed in addition to the downward feed of the electrode. If the rate of the advance is too slow, a wide overlapping bead forms with no fusion at the edges. If the rate's too fast, the bead is too narrow and has little or no fusion at the plate. The proper length of the arc cannot be judged just by looking at it. Instead, depend on the sound the arc makes. This is a sharp cracking sound, and it should be heard during the time that the arc is being moved down and to and along the surface of the plate. So a good weld on a flat plate should look like the following characteristics. Now at the top, you have an example of a good weld, and it has little or no splatter on the surface. An arc crater in the bead is approximately about a 1/16 inch from where the arc has been broken. The bead should be built up slightly, but without metal overlap on the top surface, and the bead should have a good penetration of approximately 1/16 inch into the metal base. Now, as you go down and look at the other examples, you'll see what happens whenever you travel too fast, you're going too slow, the arc's too short, the arc's too long, the amperage is too high, or the amperage is too low. Every single one of those has their own telltale signs of what's going on. What you want to do is try to be perfect as you move that along, and it takes practice, and that's one of the reasons why you don't see a lot of A&Ps welding on aircraft, is because it's a whole different skill set. Aircraft maintenance is its own skill set, and fundamentally different than a lot of other maintenance jobs that you'll see out there. Welding is much the same way. It's an art form just as much as it is a workforce trade or anything else like that. And so, while you can and you're legally authorized to weld on aircraft if you're working towards the approved data and all that good stuff, but in your own stewardship of the aircraft, you should know whether or not your skill set is up to snuff to be able to like legally and ethically and morally weld on that airplane, or if you should go out to somebody who does that for a living and actually specializes in it.
Okay, now that TIG and all arc welding is out of the way, let's talk about flame gas welding and using an acetylene torch, and what does that look like?
Okay, so just like with MIG welding and TIG welding, flame gas is going to have its own list of unique equipment that we end up having to use. We're going to start off, we're just going to go through them all. But the first off is the pressure regulator. It's attached to the gas cylinder, and it's used to lower the pressure on the cylinder to the desired working pressure, which, if you remember, is about 15 psi, because at 29 psi, acetylene can explode. So there's two types. There's a single stage and a two-stage regulator. This is a single stage acetylene regulator. And notice that it has the maximum working pressure is about 15 psi. It's a built-in safety feature. Okay, after you get the regulators, you're going to go to the welding hose that goes to the torch. Now, it's typically a double hose that's joined together during manufacture, so you get kind of a two-in-one there. But effectively, a welding hose is kind of a single item. So the acetylene hose is red with the left-hand threads indicated by a groove cut in the connection nut, and the auction hose is green with right-hand threads indicated by the absence of the groove on the connection nut, so that way you can't get them apart. And auction is always green, even whenever we get to auction in systems later on, it'll always be green. They come in different sizes, from quarter-inch to half-inch, and the hose is typically marked light, standard, or heavy-duty, plus a grade indicating whether it has oil and flame resistance covers on it. Most of the time, they'll have like a little cover that'll go over the top of it to keep anything from messing with them. The hose should also have a date of manufacture, maximum working pressure, indication that it meets specifications, and all that. So that's welding hoses. Okay, next will come the check valve, which can be the check valve stops the reverse flow of the gas that can be either installed between the regulator and the hose, or the hose and the torch. In our particular situation, we're going to say it's installed on the torch end. Excessive overheating of cutting, welding, and heating tips can cause flashback conditions, and a flashback can be caused when the tip is overheated and the gas ignites before passing out of the tip. So effectively, the torch gets super hot, and then it starts burning inside of the torch instead of outside of the torch. The flame is then burning internally rather than on the outside of the tip, and is usually identified as a shrill hissing or squealing noise. The check valve basically stops the gas from, or the flame from working its way back further backwards. Now, if the flame does enter that and start to travel back, if it got to the tank, it would explode. But luckily, we have what's called a flashback arrestor installed on each hose that prevents the pressure flame or oxygen fuel mixture from being pushed back into the cylinder, causing an explosion. The flashback arrestor incorporate a check valve that stops the reverse flow of the gas and advancement of the flashback fire. Finally, at the end, you have the torch. Now, there's three types of torches. Basically, you have an equal pressure torch, that's the most commonly used for this type of work, and it has a mixture chamber, uses a settling fuel between 1 to 15 psi, and the flame is easy to adjust, and there's less chance then of a flashback with this torch. Then you have an injector torch. Now, that uses fuel gas pressures between 0 to 2 psi. It's typically used with propane and propylene gases, so you don't have to really worry about that one in this sort of setup. And then lastly is a cutting torch. Now, the cutting torch is an attachment added to the torch handle that allows the cutting of metal. Now, that one you will probably see here or there or wherever, because if you get to a point where you just cannot get something to come apart, the cutting torch is the way to go. It basically heats the metal until it can just be just knocked off of wherever it's been attached. Now, the torch tips, they deliver and control the final flow of gases, and it's important to use their correct tip with the proper gas pressure for work to be welded correctly. The size of the tip opening, not the temperature, determines the amount of heat applied to work. If it's excessively small tip, the heat provided is insufficient to produce the penetration at the proper depth. But if it's too large, the heat's too great, and the holes are burned in the metal. So the tip sizes are designated by numbers to help you make the right decision. The manufacturer can provide a chart with recommended sizes for welding specific thicknesses of metal, and with use, a torch tip becomes clogged with carbon deposits, just like your chimney or gun barrel or whatever. If it's allowed to contact the molten pool, particles of slag may clog the tip, and this may cause a backfire, which is a momentary backward flow of gases at the torch tip. A backfire is rarely dangerous, but molten metal splattered when the flame pops. Tips should be cleaned with the proper size tip cleaner to avoid enlarging the tip opening. Finally, once we get past the torch, we have the operator. That's you. And so you need your own equipment. First off, and probably I would argue maybe the most important, is that you need some sweet glasses like this, so that way you don't burn your retinas as you're welding. Now, the goggles are to be used with any sort of welding, but this one in particular, because of the bright flame and the flying sparks, you'll have sparks going all over the place, and you don't want any of that in your eye, and you don't want the super bright light to damage your eyesight. Now, some of the styles available have individual lenses to include goggles, and some employ a whole headpiece or an elastic head strap that sits snug around the eyes for sideways protection, so that when it comes in behind the lens. Another popular style is a rectangular eye shield like this one. That takes a standard 2-inch by 4.25-inch lens. This style is available with an elastic strap and far more comfortable and better fitting when attached to a proper fitting adjusted headgear. It can be worn over prescription glasses and provides protection from flying sparks and accepts a variety of standard shade and color lenses. And the color safety lens glass is added in the front to help shade you from damage. Now, once you got your glasses on, the next thing that you're going to put in your hand is a striker or a torch lighter. Now, what will end up happening is that you'll start the gas going, you'll stick the nozzle up into that striker, and then you'll squeeze the striker, and what happens is it works just like a cigarette lighter. Like, that little rod is going to rake across that field there, and it's going to cause a lot of sparks. And as those sparks happen, the gas will light off, and then boom, you have a flame, and you're ready to go. Now, once you got a flame going, you're going to have to make some adjustments. There are three types of flames that are commonly used for welding: are the neutral, carburizing, and oxidizing, as seen here on this graphic. So the neutral flame burns about 5,800 degrees at the tip, and the inner luminous cone is produced by a balanced mixture of acetylene and oxygen supplied by the torch. The neutral flame is used for most welding because it does not alter the composition of the base metal. When using this flame on steel, the molten metal puddle is quite clear and the metal flows to give a thoroughly fused weld without burning or sparking. But however, the carburizing flame in B here burns at approximately 5,700 degrees at the tip of the inner core, and is also referred to as a reducing flame because it tends to reduce the amount of oxygen in the iron oxides. The flame burns with a coarse rushing sound and has a bluish-white inner core, a white center cone, and a light blue outer cone. The flame is produced by burning more acetylene than oxygen and can be recognized by the greenish feathery tip at the end of the cone. The longer the feather, the more acetylene is in the mix. For most welding operations, the length of the feather should be about twice the length of the inner cone. The carburizing flame is best used for welding high carbon steels, for hard facing, and for welding such as non-ferrous alloys as aluminum, nickel, and Monel. The oxidizing flame burns at approximately 6,300 degrees Fahrenheit and is produced by burning an excess of oxygen. It takes about 2 parts of oxygen to 1 part of acetylene to produce this flame. It can be identified by the shorter outer flame and by the small white inner core. To attain this flame, start with a neutral flame and then open the oxygen valve until the inner cone is about 1/10 of its original length. The oxidizing flame makes a hissing sound, and the inner cone is somewhat pointed and the purplish color at the tip. The oxidizing flame will have some specific uses. A slightly oxidizing flame is used for bronze welding, like brazing of steel and cast iron. A stronger oxidizing flame is used for fusion welding of brass and bronze, and if an oxidizing flame is used on steel, it causes the molten metal to foam, give off sparks, and burn. All right, the last component that you need is the filler rod. That's going to be the rod that you actually hold in your hand and touch down to the flame to cause it to melt and cause the weld to actually sit. But that is flame welding. Now, one place where you could actually encounter welds out in the field is with tubular airframes. Now, this is generally a general airframe or general aviation only type of phenomenon or repair procedure out there. Mostly in single engine airplanes that are made for short takeoff and landing or stall operations, like an Aviate Husky or a Taylor Craft or something to that effect. Now, with that, there comes a couple of interesting, I guess, nuances to repairing steel tubing aircraft that we need to be aware of. So first off, we're going to look at dents at a cluster weld. So dents at a cluster weld can be repaired by welding a formed steel patch over the dented area and then the surrounding tubes. So you remove any finish on the damaged area and thoroughly clean prior to welding. You then prepare a plate patch or a patch plate and cut the section of the steel, the sheet, the same material thickness on the heaviest tube damaged. Fashion the reinforcement plate so that the fingers extend over the tubes at a minimum of 1.5 times the respective tube diameter. The plate may be cut, formed prior to welding, or cut and tack welded to the cluster, and then heated and formed around the joint to produce a snug, smooth contour. Apply sufficient heat to the plate while forming so there's a gap of no more than 1 16 inches of the contour on the joint plate. Now, you can see that this operation after the plate's been formed right here on this graphic. Okay, now if damage happens between the clusters, so like you have these clusters where all the airframe comes together, and you have the straight runs. If you get damage there, then what needs to happen is it needs to be repaired using a welded split sleeve reinforcement. So the damaged member should be carefully straightened and then stop drilled on any cracks. Then select a length of steel tube of the same material and at least the same wall thickness, having the inside diameter approximately equal to the outside diameter of the damaged tube. You diagonally cut the selected piece at a 30-degree angle. 30 degrees is real important for these types of repairs on both ends so that the minimum distance of the sleeve from the edge of the crack or dent is not less than 1.5 times the diameter of the damaged tube. Then cut the entire length of the sleeve and separate half section shown in figure 547. That's right here. All right. Clamp the two sleeve sections in the proper position on the damaged area tube. Weld the reinforcement sleeve along the length of the two sides and weld both ends of the sleeve to the damaged tube. Now, that is what you do whenever there's damage in between those weld clusters on the airframe. Okay, here's what a repair could potentially look like. There's a lot going on this this graphic here, but I want you to specifically take into account the fish mouth sleeve. Now, that the reason I bring that up is that like that is the one steel tube question that is on the inspection authorization exam. And so, like, think about advanced A&P work. They're really concerned about a 30-degree fish mouth repair on steel tubes. So if you're going to insert a interior steel tube into one of these, or use one on the outside to help reinforce a broken tube and do a repair that way. That's one that you need to know, and the reason being is that it helps distribute the stress on the airframe appropriately, as opposed to creating stress one way or the other. Other terms that we need to talk about is rosette welds. You'll see rosette welds being marked on there. Rosette welds are used on many of the type of repairs that we've discussed. They're holes, typically 1/4 the outer diameter of the original tube, drilled in the outer splice, and then welded around the circumference for attachment to the inner replacement tube or the original tube structure. And that's what a rosette weld is. Okay, so aside from airframe parts and pieces, you could end up having to weld on landing gear. Now, the places that you're going to weld on landing gear are going to be kind of sparse, honestly. Most of the time, people aren't going to go out for repairs on something like landing gear because they're subject to a lot of stress, and if they break, it is almost always a catastrophic loss of the airplane. Now, but just know that like a lot of this stuff is made of steel, and it should be weldable. But you want to pay really close attention to the maintenance manual and the structural repair manual to see what damage is actually acceptable and what damage just needs to be replaced. So engine mounts is another place that you can find steel tubing that could be repaired via welding. I'll say out of all the different parts and pieces that we've discussed, this is probably the most I wouldn't say common, the most likely place that you're going to end up doing a weld repair is on an engine mount. Now, that being said, this particular engine mount goes to a Cessna 303, and it's only $1,000. So when you start looking at like potentially losing an engine or having one come off the mounts or something like that, which would be almost assured death in flight, I would highly suggest just getting an engine mount that's not repaired, that's one that's actually just in the way it came from the manufacturer, just for safety of flight concerns. But the maintenance manuals may allow a repair on an engine mount like this, and so you need to be able to at least speak intelligently to it, if not outright execute the repair. Okay, so no matter what you're repairing, if you're going to be welding, you're going to fall into one of these 5 categories, and they're pretty standard terminology for any sort of metal-to-metal joining. So you have a butt joint where two pieces of structure are butted up against each other. They touch each other pretty much equally on a horizontal plane. Lap joints. Lap basically means that they overlap each other, and that's a very, very common in the sheet metal world, so you should be very familiar with it. The T joint, obvious, makes a T. Corner joints, they come together at the corners, and that's a pretty common weld too. Most of the time, the bevel being on the inside, not necessarily the outside, but it could be on the outside. The edge joint, that means that you have 2 pieces of metal that are coming up together, and you're welding them across the top. That's going to be a little bit more rare. I don't know that I can think of a single instance where I've seen an edge joint, but I could be wrong. Maybe it's more common than what I remember. But those are the different types of joints that you could potentially see or be asked to do in some sort of welding scenario. Here we're going to look at what the weld should look like on different types of joints. So this is a butt joint, and so you notice that there's different ways to go about welding appropriately. Most of the time, you're going to be a plain or single bevel weld on butt joints, but you could have a double bevel depending on the situation, or a flange joint for that matter. But this is what they look like. Okay, so this is what a T joint looks like with a double bevel, single bevel, or plain. Remember, the beveling is basically the metal has been kind of like notched in, so that way they sit together. And then the weld is going on top of that. Not a whole lot of difference between any of them. So T joint's not really going to make that big of a difference, but that's what it looks like. All right, this is what a corner joint would look like. This you're just going to weld on top of there. There's no real single, double bevel, anything else like that. You simply just weld those two plates together on the very top. Okay, so this is your corner joints. We're going to talk about them a little bit more in depth. So a corner joint is made when two pieces of metal are brought together so their edges form a corner, a box, or enclosure, which is pretty obvious, right? The corner joint in A requires no filler rod since the edges fuse to make a weld. All right, but it's used where the load stress is not important. So it's basically just like a box, like with maybe fuel in it or something that where it's not going to put a whole lot of pressure on it. The type shown in B is used on heavier metals, and the filler rod is added for roundness and strength. And so that's like if you had like a corner piece come together on two really large pieces of metal that where strength is going to be a concern. All right, and if higher stress is to be placed on the corner, the inside is reinforced with another weld bead. So that means that basically you would weld it together and then go over it again to create a much stronger weld. And that would be indicative of a situation where you're actually welding metal or welding like aluminum on some sort of like strut or spar or something like that.